So the balanced chemical reaction would just be lithium iodide. All right, it starts off as a solid, and it just says it's dissolving in water. So it's a pretty boring reaction we're looking at here. Remember doing this stuff when it dissolves, it breaks up into its ions, and we put AQ after it. Even though it's not much of an exciting chemical reaction, it still would release or absorb some energy. And throughout the rest of this is what I'm trying to find, that question mark there. I want to know how much energy is either absorbed or released. Even at this point, you can predict the sign of the delta H. Did the temperature of the solution increase or decrease? Increase. So the temperature of the solution increased. So does that mean that the reaction itself was endo or exothermic? The reaction is going to be exo. The water experienced an endothermic event, didn't it? So from the water standpoint, it was endothermic, but from the reaction standpoint, it's exothermic. So I know I can kind of predict already that whatever I get from my delta H, it's going to be negative. I don't know the number yet, but I can already predict that's going to be negative. So I've got my balanced reaction. Now I want to go ahead and use Q equals MC delta T with this information that's given there. All right, so I'll be looking for Q, how many joules of energy were absorbed by that water. And now for the mass. All right, so this part always irritates me a little bit, but this is what gets you the right answer. If I had 100 grams of water, and then I added 5 grams of the reactants in here, I actually have 105 grams of matter in here that is warming up. So even though the lithium iodide is the reactant, it's warming itself up too. So the mass I'm going to use for these kinds of problems is going to be the total mass of the water and the reactants. So I'm going to use 105 grams because that's the total mass of both of those. And I guess I could take that to the hundredths place since they both go to the hundredths place. That's not going to limit my sig figs, but I'll go ahead and have that there. So that's different than what you did yesterday. Yesterday, the water and the aluminum were clearly separate systems, and they kept their masses to themselves. You never added those two masses together. But that's because energy was leaving the aluminum, and the aluminum had a different temperature change than the water itself had. In this case, both the reactants and the water are increasing by those 6 degrees Celsius. So for these kinds of questions with a chemical reaction in the calorimeter, you get to use the total mass of the water and the reactants. For the specific heat, we're going to assume the specific heat is the same as pure water. Occasionally, they'll give you a different specific heat, and they'll say, okay, this reaction mixture might actually be 4.12 joules per gram degree Celsius. It's going to be close to water, but not perfect. But if they don't give us a specific heat, we're going to use the specific heat of water, because that's what calorimetry is based on. And then the change in temperature, we went from 20 up to 26 degrees. So what's my change in temperature? Yeah, 6 degrees. All right, so I'm going to multiply those 3 quantities together. And that's going to be the energy that was released in this particular calorimeter. 105 times 4.18 times 6. And this isn't my final answer, so it's a good idea to keep extra sig figs as you're working through. I'm just going to go ahead and write down everything that's in my calculator, 2570.4. Now that means if you have 5 grams of lithium iodide, it releases 2,570.4 joules of energy. Eventually, I want a delta H that's based on for every mole of lithium iodide. I don't necessarily have a whole mole in there. All right, so that in red is what I would call step 2, where you're just focusing on what's taking place in that particular calorimeter. The next thing I need to do, did I say switch the sign or convert to kilojoules next? I can't remember. Flip your sheet over there, Toby. Okay, we'll switch the sign. Either order works, but let's switch the sign. So I'll call that step 3. So now the Q for the reaction is going to be exothermic 2570.4 joules. All right, so you switch your sign. So now we're focusing on the reactants releasing the energy. Reese, are you getting a slightly different number for your Q there?
Yeah, I am.
What did you get?
I got
I think
2633.
I'm going to use that. I typed in 4.08. 2633.
Yeah.
Thank you. I noticed you guys over there. Was there a decimal after it, Amelia?
0.4.
Okay. Doesn't hurt. I'm looking at my calculator. I've got 4.08 instead of 4.18. We switched our sign, and now we remind ourselves it's exothermic, and that matches that our prediction for delta H was going to be a negative delta H. All right, so that's what I call step 3 there in purple. I'll do green for step 4. Will, what does step 4 say on that other side? I can't remember. Okay, well, let's convert it. That's going to be pretty easy. We'll divide by 1,000, or basically just move that decimal 3 places there. So I can still say Q for the reaction that's inside that calorimeter is negative 2.6334 kilojoules. And again, that's the kilojoules for every 5 grams of product. But we don't write delta H as based on 5 grams of, I should say, reactant, not product. It's not based on the 5 grams of anything. It's going to be based on a mole of something. So now I've got one more thing to do, which is to divide by my number of moles. So your delta H for a reaction needs to be in however many kilojoules divided by for every mole. So per means for every 1 mole. All right, well, I know my kilojoules already from before is negative 2.633. But I need to know how many moles I have Do we know a way, could we convert that 5 grams of lithium iodide into moles? Yeah, we can do that. So let's do that right here on the bottom. I'll fit it in. 5 grams of lithium iodide when every mole of lithium iodide is just the molar mass of it. I think it's 6.94, but I can't quite see it from over here. Yeah, so lithium 6.94 plus iodine 126. Just a reminder how I'm getting older. I used to be able to see every number on there. Now I have to walk over to it. It's blurry. All right, 133.84. All right, so let's do that. 5 over that molar mass. That's 0.03736. And that's what I'm going to put in here for my kilojoules per mole. So we can see it's just a ratio that we're assuming stays constant here. If I had 0.037 moles, I would release 2.6 kilojoules of energy. So now when I finally do that division to get my final answer, it's going to be on a per mole basis. I'm just going to keep all those decimals in my calculator there divided. Negative 2.6334 divided by the number in pink there, 0.03735. Thank you. Yeah. All right, so I'm getting negative 70.5. If I go back up to my original problem, never mind, I'm probably limited to 2 sig figs throughout because of that 5 grams. So I'll call it just negative 70 kilojoules per mole. You say 70 or so?
Why not make it 71?
So I kept all the digits in my calculator, so I've got negative 70.487. Does yours say negative 70.5? Anybody's?
Just wrote it down as negative 70.5.
Oh, okay. I did say that out loud, didn't I? So when I did the division, sorry, I'm seeing all the numbers in my calculator, just assuming you can see everything I see. When I did the number in my calculator, I am getting, it's negative 70.487. Write it sideways here. So out loud I said 70.5, but really the 4 is the next door neighbor. And so at 2 sig figs, I'll go with negative 70. I should have passed out the calculators first. And that's kilojoules per mole for this reaction. I'm going to pass out these calculators now.